Okay guys, in this video what we'll do, we'll have a look at the alkenes, and this should help you with one of the worksheets as well. So this is the next family, if you like. So we're going through the series of families. The alkanes, some of the, if you like, the simplest organic family, and then we look at the alkenes. Look at the, it's not a huge transition into this family. The difference is this double bond right here. So the double bond, you see, alkenes have got a double carbon-carbon bond. And now you need to think of, it shouldn't be that strange to see two hydrogens off this carbon now, because remember, every carbon needs 4 bonds. If it already has has a double bond, 2 bonds if you like, to another carbon, that only allows it 2 other bonds, if you like, to a monovalent or hydrogen, which is 1 monovalent, meaning 1 electron in its outer shell, if you like, or willing to partake in bonding, a single covalent bond. So you see, hydrogen only will join 1, and that's why, if you like, the first member is C2H4. Now you'd have to think about this. There's no such thing as methene. How could you have methane? That would mean 1 carbon double bonded to what? So if you like, because alkenes, what makes them alkenes, Ene, this Ene right here, what makes them Ene, if you like, is the double carbon-carbon bond. So obviously the minimum number of carbons you need is 2, and if you remember about the prefixes, eth is 2 carbons, and that will never change. That's the great thing about organic chemistry. It seems much more complicated than what it is. Like prop will always be 3 carbons. You can look that up when you're on the side of deodorant cans or anything. You see compounds in them. Like these are not changeable words. But will always be 4 carbons, and that's something you already know about the molecule then just by seeing. Pent is 5. So the double, that's the only thing that's really new. The other thing is the formula. That should be formula. That the homologous series, or the form of a homologous series of formula CnH2n. So you see, for every carbon, that's for every 2 carbons would be the minimum, obviously. There'll be 2 times 2 would be the first one, which is 4. And that's how you get C2H4 down here, you see. And the next there's some more members, ethene. Now to be honest, instead of drawing out this, normally you would draw ethene to try and show that each hydrogen will be as far away from every other hydrogen as possible. You would spread them out like so, you see, rather than maybe in the diagram. So you'd bend them so that they're as far away from each other as possible. But the double bond, now this is not easy to draw on this thing, but the double bond is right here in the middle, so never forget that. That's what ene is. And eth is still 2 carbons, prop is still 3, but is still 4, pent is still 5, hex is still 6. But as you see, double bond, double bond, double bond, double bond, ene. It is an alkene. They are said to be unsaturated. Now what that essentially means is that if you thought about it, sometimes people just say that an unsaturated compound is one that has a double or triple bond. But like if you think of the word saturated in sponges, like a sponge is saturated when it cannot possibly hold any more water. Well, you see, this is not saturated or unsaturated because potentially it could hold more hydrogens if we broke one of these bonds. And then not to break up the molecule now, just to break one of the 2 bonds that makes up the double bond. So one of those bonds is weaker than the other. And the reason for that is, of course, that goes back to how molecules or carbon-carbon bonds. So I'll give you the simple explanation for this perhaps. If you think about carbon, its bonding orbitals are the p orbitals. So there's 1 carbon and there's another carbon. The first bond that is created is the head-on overlapping of 2 p orbitals, 2 dumbbells right here. So you have a carbon, and then if you draw 1 p orbital facing, and then look at, there's the overlap. And there's the 2 electrons, and that would be a single carbon-carbon bond. Now when you try and create a double one between these 2 carbons, that's this one here and this one here, 1 and 2 there, you see we can't force the electrons on top of each other. As you know, electrons do what to other electrons? They repel. Therefore, the next pair of electrons that is shared between these 2 atoms, involving the overlapping of p orbitals, is up here, if you like. They only side-on overlap. And that weaker bond is known as a pi bond. But when they're head-on, which will obviously always be the first bond created between 2 carbon atoms, it's stronger, that's known as a sigma bond. Now it's written as sigma as in the word sigma, but there's my poorly illustrated the symbol for sigma, and that pi, from maths, that's a pi bond. So you need to think about that. Why are they not on top of each other? Why can I not just draw one? There's one, that's 1 carbon with its dumbbell overlapping, dumbbell P-shaped p orbital. There's the 2 electrons, rather than us drawing the simpler structure of 2 electrons being shared between 2 carbon, like this. Well, you see, that's Bohr model. Now we're more modern. We can show orbitals overlapping, because we know that these lines in the Bohr model just represent an amount of energy. They don't actually represent the location of electrons. That's what these things do. Now, just to remind you, the p orbital has this shape. There's 1, 2, 3. You see, there's 3 p orbitals, 3 dumbbells, and that's 1 carbon, if you like, and then you put another carbon beside it. So I'm only down here, I'm only drawing 1 or 2 carbons with 1 orbital each. See, if I can't squish them on top of each other for no other reason that these electrons here that are being shared by this carbon and this carbon can't gel in on top of the other. So therefore, instead of a head-on overlap, there is side-on overlap. And that is known as a pi bond. And the stronger, not a huge amount, but certainly stronger, sigma bond is created there. And that is a really important thing. I mean, that's a lot in this video. If you understood and you could draw the overlapping of p orbitals, that would be very strong. The first alkene is called ethene, as we said. The second one is propene, butene. These become quite repetitive now, and the worksheet will help you do this. The 4 carbon atoms allow for different structures. See, that's the thing. If you look at this one, there's 1, 2, 3, 4. You see, you could have a double bond there, or you could have one here. Now you need to ask yourself the question, why am I not circling this one over here? Why am I not saying that you could also have one here? And you need to think about why that is the case. Think about it. If the double bond was moved from this side over to here, this side right here, then you would need to think about that for a second. That would be the same location. Remember, and it's so easy in organic chemistry to forget. These molecules are 3D. If you make the molecule with a double bond in it, and that double bond is moved, you need to be careful. You need to be really, really careful that you don't lose the chemistry behind it and say to yourself, well, and I'll show you what I mean now as I make this molecule. So there's the double bond. And then if we had some hydrogens off that one, and then we'll get some hydrogens. You see there, what is the name for that? That is, of course, propene. But it's like, if the double bond, it's a molecule, it's 3D, no one can say that it has to lie one way or the other. Whereas the one on the board, or the one on the data projector at the moment, that has one more attached to it. And that one is known as butene. But if you think about the arrangement around butene, butene has a structure where you could have the double bond like the bottom diagram there with a double bond. That's that molecule. And you think about how it'll be twisted to try and keep the electrons as far away from each other as possible. And you see that there's a big difference. There's the double bond. Now, but it would also be possible for that double bond to be at the end and for it still to be butene. You see? It's still butene. A double bond, 4 carbons. Ene, E-N-E. But now the double bond is in the end. Whereas if I rearrange them once more, there's the double bond, now it's in the middle. But if I move that double bond over here, obviously it's still the same molecule. Like if I go from that side and I switch it around and I put that one on the end, you need to think about that now. Like if you draw it like that or you draw it like that, it's still the same molecule, you've just rotated it around. So the big emphasis here is that you have two, but you do have two possible locations. On the first and second, between the first and the second and third. Or if you put it over here, you would then number it 1, 2, so it's still between the first and the second, because you can number from any side, remember from yesterday. So there's the two structural isomers. Now the way you would name those is what you say is you name the first carbon. So like for this one right here at the bottom, that will be considered, or let's do the top one first. That will be considered to be but. So that's the but part. And then indicate where the double bond is. So the number 1, ene. You see? Now you only indicate this when there is more than one possible. So but 1 ene would be this top one. And then if you took this bottom one here, 1, 2, 3, 4, number it left to right, then number it right to left just to check. 1, 2, 3, 4. Well, remember the lowest number here is 2, so that would be considered, it's still but. So it's still but. The only difference is it's but 2 ene. You see, so the double bond starts, and that's the big thing. It's where the double bond starts, the carbon that the double bond starts. Keep that as low as possible. And that's how you do it essentially. There's nothing more complicated than that. It ends in ENE again. The longest carbon chain. I'm not going to go through all that again. Always use the longest carbon chain and then C. So there, that's but 1 ene. Why do we have to put the 1 in here? That's because it could possibly be on the second one and be a different molecule. Now obviously if it's on the third one, you're back to the same molecule, it's just flipped over. Be careful there. That's but 2 ene, you see. Indicated with the 2, where the double bond starts. It doesn't matter, you could still number from this side, it would still be but 2 ene, remember, because that would be number 2 then. There's no but 3 ene, of course, because that would be back to, like, you can't, we're putting in these numbers, I mean, they do work, but it's real life, you can't flip it around and you know, expect it to be a different molecule. These are 3D in space. And pent 2 ene then has a double bond between carbon and there's a nice example. You could have it between the first and the second and the third. Why would I not say there's no pent 3 ene? Because remember, if I put a double bond there and take away this double bond, it's the same molecule. I would just neighbor it 1, 2, 3, 4, 5. You see? It's now between 2 and 3 again, still pent 2 ene. And if I took that one away and put the double bond here, it would be back to this first one. 1 that starts on the first one. So you need to look at these now and just think about them in terms of, look at hexene is 3 possible. But this is probably a bit high for Lebensjahr, but you can imagine. But again, there's only 3. There's no hex 4 ene because you'd be back, you would start naming it 1, 2, 3, so it'll be back to the 2 ene again, hex 2 ene again. So you need to think about that. We draw these molecules on a page, but they are 3D and you can flip them around. So just be careful on that terms, and so on and so on. This is a nice preparation of ethene. We'll look at that again, but that's plenty for this, for the introduction of the alkenes. Ene, double bond.